So in this video I just wanted to talk a little bit about units. Units are very important. They basically make everything we do make sense in terms of you can't really understand a value without understanding its unit. Because, you know, how long did you wait? 7. Well, that could be 7 microseconds or 7 days without the units on the end of it. So that's why units are so important to us. So, as scientists, we have a base set of 7 units for which all other things are derived. So we are working in the metric system, and we work with everything derived from a combination of these 7 units. And I would dare say that we could probably go as low as 6, because candela is practically never used. I've never seen it used in all of my years as a scientist. So we have our units of length, mass and time, which are our perhaps 3 most common, certainly the 3 that the layman would know. And then our other base units are our unit of current, temperature, which is our absolute temperature in Kelvin, and this should be a capital K, sorry, capital K, and our amount of substance in moles. Everything else derives from those. So we can see this is just a table, just of a selection of different quantities that we're measuring here. And we can see that whilst they might all have their own unit that we think about, so power is measured in watts, or, I don't know, resistance is measured in ohms, these values are all derived from other things that's going on. So we can see that actually our watt is a kilogram meter squared per second cubed. So it's based on our set of 7, or 6 of the 7, that we had before. So everything can be written in terms of these units. And we can start to see perhaps some strange ones, some ones that we don't necessarily immediately recognise. So things like electric potential, here, a volt, actually is the unit of the kilogram meter squared per second cubed per amp. They're all based from what's gone on before. So here I've just got just something to kind of break some of this down for you, so that we can think about the unit of energy, which is normally given to us as capital J, or the joule. And if I look on the previous slide, my unit of energy, the joule here, is the kilogram meter squared per second squared. Well, if I just think of a couple of equations that have an energy term in them, so I perhaps might know the equation E is equal to a half mv squared. This is the kinetic energy of a particle. Or I might also be able to think that E is equal to mgh, so mass times the acceleration due to gravity due to the height that it's raised. Well, I can show that both of these in fact have the same unit. So if I think about this in terms of, well, what's my unit of mass? Well, that would be my kilogram. And my unit of velocity, well, velocity is how far I go in a second. So this is going to be meters per second, and that whole lot is squared. And so this comes out as a kilogram meter squared per second squared. So my unit of energy is a kilogram meter squared per second squared. If instead I use this one here, E is equal to mgh, in this case I have my mass, again in kilograms. G is the acceleration due to gravity, so an acceleration has the units of meters per second squared, and h, the height through which I raise it, would have the units of meters. So once again we can see that I have the same units no matter what my term for energy is, which kind of makes sense, because energy is surely always measured in the same units. It's got to have the same base units. And this kind of process that I've gone through here is called dimensional analysis. I've kind of shown that it's dimensionally consistent. Now, often in chemistry, we use units that aren't just, say, a watt or a joule. We tend to use units for things like enthalpy of, quite often, a kilojoule per mole, or in the terms of our entropy, we usually have our molar entropy of joules per Kelvin per mole. So here I just have entropy, and here I've got my molar entropy. So these are actually kind of what we would normally consider to be combined units. I've taken more than one unit and put them together, and these are the ones that usually makes most sense to me in terms of what I see in chemistry. So what are my rules about units? Well, first off, I can only add and subtract units which have the same, or values that have the same units. So anywhere in an equation where I see two terms added, so for example, delta G is equal to delta H minus T delta S. In this case, delta H and T delta S have to have the same unit. And so if we think about this, well, normally delta H is measured in kilojoules per mole. Delta S is normally measured in joules per Kelvin per mole. And T is normally measured in Kelvin. And so my kelvins and my per Kelvin cancel. And so I can see that now I have things that are essentially in the same unit in terms of I've got kilojoules per mole here, joules per mole here, which means that I'm going to need to basically get rid of this kilo. So multiply this one by 10 to the 3 so that I just end up with it in joules per mole. This is a trap that some people fall into, thinking that they can do this all in one step. So just always remember that it's not quite as simple as always being in one unit. I hope this video has been helpful. Please let me know if you want any more.